What's inside Mars? We know a lot about what's inside Earth. But at Mars, we've only just scratched the surface. To learn how Mars formed, we have to study its deep interior. NASA's InSight lander was designed to do just that by taking the planet's vital signs. Listening for its pulse or seismic activity, including any Marsquakes. Taking its temperature to see how much heat is flowing out from deep inside. And checking its reflexes to see how much the planet wobbles as it whips around the sun. These all provide clues to what the planet is really like inside. So what's inside Mars? InSight can help us find out by giving Mars its first thorough checkup since it formed 4.5 billion years ago. The more we learn, the better we'll understand all the rocky planets and the history of our solar system. How did Mars get such enormous mountains? Mount Everest may be the ultimate climbing challenge on Earth, but it has nothing on the volcanoes of Mars. Olympus Mons on Mars is more than twice as tall. How did these mega mountains form? Early on, Mars had really active volcanoes fed by hot, rising blobs of rock from deep inside. But Mars doesn't have tectonic plates that move over hotspots, like in Hawaii. So instead of getting a chain of volcanoes, you could keep building one huge one. And with the lower gravity on Mars, that magma could be pushed to great heights. On any planet, a lot of what it looks like outside is tied to what goes on inside. Studying how heat flows out from a planet can tell us a lot. NASA's InSight mission carries a special probe to burrow down and measure heat flow. That can teach us not just about how Mars works today, but how it and all rocky planets form, including Earth and even planets in other solar systems. Are there earthquakes on Mars? Or rather, Marsquakes? Quakes on Earth happen many times a day, largely due to continental plates shifting as they float on the mantle below. That's called plate tectonics. Mars doesn't seem to have plate tectonics, but other things can make the ground shake too, like cracking caused by contraction from cooling, magma moving and creating pressure deep underground, or even meteorite impacts. Quakes of any kind send seismic waves around and through the planet. Scientists can study how those waves bounce off layers deep underground to help understand what a planet's interior is like. NASA's InSight lander carries a super-sensitive instrument to measure Marsquakes and could detect dozens of them during its mission. Each one can tell us a lot about what's going on inside that mysterious red planet. Maybe about how all the rocky planets came to be. How do you get to Mars? If you want to send a spacecraft all the way to Mars, first you'll need a fast rocket to escape the pull of Earth's gravity. The heavier your spacecraft, the more powerful your rocket needs to be to lift off. Next, make sure you launch at the right time. Mars and Earth orbit the Sun at different speeds and distances. Sometimes they're really far apart, and other times they come closer together. About every 2 years, the two planets are in perfect positions to get to Mars with the least amount of rocket fuel. That's important. The total trip is over 300 million miles. Finally, make sure your aim is right. You can't shoot for where Mars is at launch time. You have to aim for where it will be when you get there. It's a lot like how a quarterback passes a football. Also, you may need a few thrusts to correct your direction along the way so you don't miss Mars. If all goes well, you'll get to the red planet in about 7 or 8 months. Then, if you actually want to land on Mars, well, that's a whole other challenge. How hard is it to land Curiosity on Mars? On a scale from 1 to 10, landing on Mars is a 20. Curiosity is the biggest, most capable Mars rover yet, and needs a new type of landing to reach the ground safely. In this 7-minute trip to the surface of Mars, we have to slow down from over 13,000 miles an hour down to 0. Hundreds of things have to go just right. Curiosity must hit the atmosphere at just the right angle, endure extreme heat from friction as it descends through the atmosphere, open its parachute at just the right time, use radar to know exactly how high it is, free itself from the parachute, perfectly fire 8 rocket engines to slow final descent, drop down dangling on 4 cables, lock its wheels into place just before landing, and cut the cables right at the moment of touchdown. And even if we do everything right, Mars can always surprise us. It's a big challenge, but a big opportunity to help unlock the mysteries of Mars. How do you choose a landing site? So you want to study Mars with a lander or rover, but where exactly do you send it? It's a tricky question for engineers and scientists. You want it all, to land, work, and discover. To land safely means no high elevation sites where there isn't enough atmosphere to slow you down in time. And try to avoid places with steep slopes or big rocks that could damage something. You also don't want to sink into a thick layer of dust. Working is easier near the equator, where seasons aren't so extreme and where solar panels can get lots of sun. And of course, don't send a rover somewhere it can't drive. Most important is what you want to discover. Some sites are great for studying rock layers, others might be perfect to listen for quakes. Using Mars orbiters, you can collect lots of data on potential sites. When you find the best spot to land, work, and discover, you've found your new home on Mars. How do you land on Mars? Very carefully. Your spacecraft hurtles toward the planet at thousands of miles per hour, so you'll have to hit the brakes in a hurry. First, your capsule needs a heat shield. It protects the spacecraft inside from the heat and friction of entry into the atmosphere. Friction slows you down over 90%, but not enough to land safely. Use a parachute to slow down even more. Still, falling at over 100 miles per hour, you need the right system to land safely. Here are some options. With a small to mid-size rover, use a cushion of airbags along with retro rockets. Impact at 30 miles an hour and bounce to a stop. With a large lander, use retro rockets and landing legs to touch down going about 6 miles an hour. Or with a large heavy rover, use a big jetpack to slow down to under 2 miles an hour. Then gently lower it on cables to land on its wheels. Any way you do it, you'll need skill and hard work. There's nothing easy about landing on Mars. Curiosity looking for organics. Organics are carbon-based molecules, key ingredients to life. If Curiosity finds organics in ancient rocks, there's a better chance Mars once had good conditions for small life forms called microbes. But finding organics is hard. That's because organics easily break down when exposed to harsh things like extreme radiation and chemical oxidants that gave the Martian surface its rusty color. A great place to look for ancient organics today is in rock layers. Organics that were quickly trapped and buried in layers of mud or in sediments that sank to the bottom of a body of water could have an especially good chance of being preserved. Scientists think Curiosity's landing site, Gale Crater, contains those special layers, created in ancient times when water was present. The water dried up long ago, but rock layers that remain today could still preserve organics inside. If Curiosity finds organics, it wouldn't prove life existed, but it sure would improve the odds that Mars once had the right ingredients for life. How do rovers drive on Mars? First of all, there's no joystick for driving a Mars rover. Before a rover hits the road, engineers send computer commands overnight, telling it where to go the next day. Depending on how tricky the terrain is, rover drivers have two options. They can send a string of specific commands like, drive forward 5 meters, then turn right 90 degrees. The rover turns its wheels enough times to add up to 5 meters, and then turns in place. Or if it looks safe, they can let the rover think on its own. They write commands like, see that rock over there? Find your way there safely. Then, using two cameras like human eyes, the rover gets a 3D view of hazards such as large rocks and steep slopes. After mapping the danger zones, it plots the safest route to avoid them. Either way, did the rover complete its drive as planned? Engineers double-check when the rover sends back a postcard of its new spot on Mars. After 7 dramatic minutes of entry, descent, and landing, everyone will want to know, did Curiosity survive? There's a possibility we won't know, at least not right away. During its descent through the atmosphere, Curiosity must switch to a new antenna for each transformation it makes. At each switch, we could lose lock on the signal for a short time. That won't hurt the rover, it just means we won't know what's happening right away. Even with a solid signal, the communications link direct to Earth only works during the first half of the rover's descent. Why? Like Earth, Mars is spinning, and during landing, Curiosity and its landing site will disappear from view like the sun setting. Out of sight equals the end of direct radio contact. But NASA has 2 spacecraft orbiting Mars that can help. For the second half of Curiosity's descent, the Mars Odyssey orbiter is in a good place to pick up the rover's signal and send it right back to Earth. To best hear Curiosity's signal, Odyssey must rotate about an hour before landing. That sounds easy, but engineers are asking Odyssey to perform a maneuver it's never tried before. Will it work? Probably, but it's not a sure thing. If Odyssey doesn't rotate successfully, never fear, the rover won't be affected whatsoever. Once again, it just means we have to wait longer to hear from the rover. Odyssey could perform as hoped, but we're still not home free. Engineers always think of what-ifs. For instance, what if the rover lands on a slope? If so, the low-flying Odyssey orbiter might not be able to pick up its signal. Even if everything goes according to plan with Odyssey, there's a final challenge: time. The rover may be standing safe on Mars, but Odyssey has to be quick in getting the signal. Odyssey is moving fast. It will only be in the line of sight to hear from the rover for a few minutes, perhaps no more than 5. So the Mars Reconnaissance Orbiter plays the role of backup. It will also fly overhead to capture what happens and then store the landing data it collects on board for playback to Earth a few hours later.
Engineers then have to decode the data, which takes several hours. Sometime in the middle of the night for Curiosity's mission team, it's possible that the orbiter could tell us the rover's fate. Or there are other scenarios where the rover might be perfectly safe, but we might not hear from it for 3 days. That's all to say, Curiosity's landing is filled with drama, and will need lots of patience. No wonder they call this rocket science. What happens when the sun blocks our signal? About every 2 years, Earth and Mars wind up on opposite sides of the sun. That's called solar conjunction. It's like being on either side of a huge bonfire. We can't see Mars, and our landers, rovers, and orbiters can't see us. If our spacecraft send back signals, charged particles from the sun could interfere, causing gaps in the data that reach us. That's not a big deal. If something's missing, it can always be resent later. But no way do we want to lose data when we send up commands. Receiving a partial command could confuse the spacecraft, putting them in grave danger. So mission controllers plan ahead by sending up simple to-do lists, including regular health checkups. Back home, this break in communications lets team members catch up on other work, or take a well-deserved vacation. Solar conjunction lasts just a few weeks, then it's back to the grindstone, on Earth and on Mars.